Okay, guys, thank you everyone who is here. Turned in homework set number 4. It was about, I think it was pretty much just about the implicit function theorem and how to use it. It had a sort of modeling aspect to it in question 2. And I think that's maybe, I know because some people have emailed me that they are having some trouble, like, just deciding what to do with the equations that you have. You have equations, but you still have to know what to do with them. And I'm very willing to talk to you now about that, since you turned it in, and you can ask questions, and I think it'll make sense. I think this is something I can explain. And if you have any questions, I should be able to answer it. Let's see what we have here. This is the homework. Oh, shoot, I don't have the answers typed up, but I think this will still be good. I'll just give them to you now, or at least talk about them now. Okay, so here's, I don't know how to make this. I had this issue last time. How do I ignore the stuff here on the side? I don't know how to do it. Do we want to talk about question 1? I think question 1 was easier because you're given this function very directly, I want to say explicitly, but that means something else here. To show that there exists an explicit function z x y, what do you have to do? You have to take the partial derivative of f with respect to z, right? Did you guys do that? Hopefully that's pretty easy. F of z is what in this case? X squared y times, I'm sorry, plus y, and oh, now you have this term here. It's going to be a 2z over, is this what you got? 2z over x squared plus z squared. Okay, that should be what you got, right? For fz. Does that look right? Is that what you got?
Yep.
And then you plug in, whoa, x equals 0. That's good. That means this term goes away. Y equals 5. So there's a 5 there plus, so what do we get? We get 5 plus 2z. Z is -1. So it's -2 over x squared is 0. Z squared is 1. So it's 1. It's 5 minus 2. I think the answer is 3. You guys get 3 for f of z? And that's enough for part A. Part A, you just have to show that that's not equal to 0. If you said that, I would accept that as a full credit for the answer. It'd be even better if you said something like, oh, because because this function capital F is continuous and differentiable with the variables x, y, and z in a neighborhood of 0, 5, -1, then that plus the fact that fz is not equal to 0 is enough to solve A. But to do B, now, it's nice that I already have f of z, because now we just need to find fy. I keep saying of, it's not of, it's just, for shorthand here, it's fy. What is that? X squared z. Is that what you got? X squared z. What else has a y in it here? Plus z. Luckily, the last thing has no y in it, so that's it. I plug in x equals 0, that goes away. Z is the only thing that's left, and it's -1. Does that seem right? So use the corollary to find the exact value of this. The answer is negative fy over fz, which is 1/3. You agree? You see how I got 1/3?
Yes.
No questions about that? Okay, good. I suspect your questions will be about part 2, so let's do part 2. I'm going to clear my drawings. Not part 2, question 2. Hey, why can't I go down? Here we go. All right, so this one's a little tougher. Eliminate cy is my, by the way, can I talk, this is something that, it's more part of the class. I guess Jordan should be here for this, but it's his fault that he's not here. I just want to say a little bit about, did it again, about this, this series of equations. This is actually a really fundamental macroeconomic model that's just, it's almost like an identity. You know what I mean by an identity? As opposed to, a formula. A formula might be something where here's a way to calculate this thing. It's a formula. Whereas an identity, it's also a formula, but it's sort of, it's like a way to identify. It's a way to define in some way what a variable is just by breaking it up into its constituents. So capital Y here is total national income, all of the stuff that the nation produces in dollar form, measured in dollars, that's capital Y. What is that equal to? Whatever the total consumption of the nation is, plus whatever the total investment of the nation is, plus whatever the total government expenditure of the nation is. This is sort of identically true. It's not true because of some behavior. It's true because of that's how it's just a way to split up Y into these three components. You know what I mean? So that's like that's a very fundamental equation for national income. How about this second one? This is also a very fundamental equation. What is it saying? The total income of the nation, Y, minus the taxes. So now we're thinking of people, the people who earn this income. They earn Y, and they have to pay T of it in terms of taxes. So Y minus T is everything that people have left over after they're taxed, is equal to their consumption. Of course, what do you do with the money that you have? You either consume it, that's CY, or you save it, SY. And pretty much that's the only two things you can do with it. So this is also an identity. And okay, so this model is like, okay, what if we take these two identities and try to solve for some equilibrium condition for Y? Now you would be justified in complaining by saying, you've given me 1, 2, 3, 4, 5 endogenous variables, and you've only given me 2 equations. You told me the first week of this class that you can't solve a model unless you have as many equations as there are endogenous variables. And I would say, yeah, you're right. You can't solve for Y explicitly in terms of things that have no Y in them. You can't. I simply haven't given you enough equations. But that's kind of the beauty of this new method that I'm teaching you, which is, wait a second, even if I can't solve for Y explicitly, I can still learn something about it. I can learn first, like part B, show that Y star as a function of G0 does exist. And you can even tell what its derivative is. And you can even tell what the sign of the derivative is, positive or negative. So that's what I asked you to do for this homework. Any questions about that? Like what even I was asking you to do? Yeah, so I mean, it's kind of good if you study more macroeconomics. Of course, you'll have these equations and then build even more on top of them. Like you'll talk about how investment and capital evolves over time. You'll talk about more complicated things. So this is just like a basic thing that macroeconomists would talk about. But you can still get some interesting math. Let's do it. Eliminate CY from the model. Of course, you could take either of these equations, solve for CY, and plug it into the other one. Once you do that, you will find a Y on both sides of the equation. What do you do with that? Just eliminate Y. It's okay. It's okay to not have a Y in there. If you can see here, using I, S, T, and G. I didn't say you had to have a Y in there. So that's what you'll get for part A. Let me just write it out here so you can see it. For part A, you should have gotten something like, maybe I'll write it above. Maybe I can write it here on the, right here. So here's a big white space here. What should you get? Let's plug CY. Let's subtract SY from both sides and get, Y minus T minus S equals C, and plug that in for this. You'll get Y equals not cy, but y minus t minus s plus I. Sorry, this is poorly written. I'm gonna make it bigger and more clear over here on the side. So once you do this and eliminate the y's, oh, by the way, it doesn't matter if these are negatives or positives. You know, you can multiply the equation by -1 if you don't like having, well, 2 of these terms will be negative and 2 will be positive. So I guess it doesn't matter. What will you get as an answer for part A, this equilibrium condition? It should be this. Wait, why do I start with 0? I don't like that. Let's make it look like the rest of our implicit functions and move everything to the left side of the equation. And on the right side of the equation, we'll just say equals 0. That's like the normal thing to do. So let's take this, eliminate the y's, and move everything to the left, and what's on the other side will be equal to 0. So here's what we get. You want me to put the of y star? I'll put the of y star. I'll probably have enough room. Oh, by the way, why is it y star? Because it's the y that solves this equilibrium condition. It's not just any old y. It's the y that solves the equilibrium condition. So it's good practice to put the star there. S of y star minus, gosh, I can't read my, oh, this first was a t. Dang it. I'm sorry, guys. This should have said, this is a t on this side, an s on this side, a negative and a negative g0 is what I was intending to draw. Let me try that now. T of y star plus s of y star minus I of y star. And then minus g0 equals 0. Okay, so I think that's an answer for part A. If you had this same equation but rearranged somehow, like maybe negatives on every, that's fine too. You could have this equation rearranged in some way, as long as it has these 4 variables with this relationship. I would count that as correct for part A. Okay, for part B, use the IFT to show an explicit function y star of g0 exists. Well, this whole thing is f, right?
Professor,
Sure.
how is t positive? Or my t ends up being negative. I probably did something wrong.
Well, if t and s are negative, then I and g should be positive. Is that what you have?
Yeah. Mm-hmm.
Yeah, that's fine. It's okay to say negative t minus s plus I plus g0 equals 0. That's exactly the same equation, just multiplied by -1.
Okay.
Yeah, I would count that correct. That's correct.
All right. Sorry. Thank you, Professor.
No problem. All right. We're trying to do this. Show that y star g0 exists. What do I need to do? I need to find f, the partial derivative of f with respect to what? With y star. Hopefully you guys got this. This was the not easy thing. You needed to think about B and say, okay, what am I taking the partial derivative and with respect to what? The answer is this entire left-hand side of the equation here, once you solve the equilibrium condition, that entire left-hand side, I want to take the partial derivative of that whole thing with respect to y star, because y star is the variable I'm trying to define as a function. So just like in part 1, we need to show that that's not equal to 0. Okay, well, what is f of y star? Well, we have f, the derivative of t of y star with respect to y star is simply something you can call t prime. I've told you to do that here. Let c prime, I prime, s prime, and t prime represent the derivatives of CIST. So let's just call that t prime. You get that? T prime is the derivative of t with respect to y star. How do you know it's with respect to y star? Because that's the only variable inside the function t. Okay? Plus s prime, that's the second term, minus I prime How about this G0 term? Well, that doesn't have a y star in it. So that doesn't exist in f of y star. This should be all you have for f of y star. I say of, I don't mean of. F sub y star. Okay, what do we need to show that that's not equal to 0? How can we show that? How can we show that? No, I should have kept annotate on. Let's look at annotate. Look at this equation. Look at this condition right here that I've given you. Yeah, s plus t is greater than I. What does that mean? It means these two terms, these first two terms, are greater than I. So t plus s is greater than I. Something greater than I minus I has to be positive, which is not 0, which is an answer to part B. That's how you solve part B. Okay, you just say that f sub y star is equal to this term, t plus s minus I. And because of this condition, which I put right at the end of this question, we know that this first term, two terms, are bigger in absolute value than this last term. Therefore, the whole thing has to be positive and not 0. And so we're good. Do you guys understand how you answer B? The answer to B. Oh, yeah, you do good. Yeah,
I answered that. I just messed up when I eliminated c of y and set them equal. Something with my math. I think I just rushed it and I didn't eliminate y, so my numbers were messed up. But
even if you don't eliminate y, I think it's okay. Like you may have a y on both sides of this equation, right?
Yeah, I eventually was able to figure out because of s prime and t prime, that it has to be positive. So, but it just was different.
Yeah. So let's say you had a y on both sides of this equation. Remember though, when you want to use the implicit function theorem, you have to move everything over to the left side. So even then, even if your answer for part A had y's on both sides of the equation, that's probably okay. But in part B, because you're using the IFT, you would have to move everything over to the left, and that's when the y's would have to cancel. You have a plus y and a minus y, they will cancel. Okay, so I mean, I think it's okay if your y's don't cancel in part A, but they really should for part B, if you do the algebra correctly.
Yeah.
Okay, great. All right, so we're not done yet. That's part B. For part C, now we need to not just learn what Fy star is, we need to learn what F sub G0 is. Luckily for us, this is actually really simple, right? I mean, dy dg0, well, all I need to know is the implicit function that is the relationship between y star and g0, and take the partial derivatives of y, we've done that already, and the partial derivative with respect to g0. That's what we need to calculate now. What is it? This has no g0, this has none, this is none. This is the only g0 in the whole thing. And it's negative, so the derivative is -1. That's it. So what is dy dg0? The answer is, here, I'll write it out a little bit more formally, equals negative f g0 over f y star. Some people emailed me and I didn't tell them this exactly. I gave them hints. I said, well, for part C, you need to calculate it as the ratio of the proper derivatives, and it's up to you to figure out which ones they are. But this is how it is. It's just like before, you kind of cross like this. Okay, Jordan's there and he's waiting. So, but we're almost done. This is good. Now I just need to plug in what I found here for fg0 is -1. Notice I have a negative here and a -1 here. I'm going to already cancel those out and just put a +1. F of y star is this thing on the bottom, t prime plus s prime minus I prime. Should I put the serifs on the I? It looks a little bit better with serifs. Okay, that's the answer for find dy dg0. We found it. It's here. How about this part? Determine its sign. Well, luckily, we just figured out that t prime plus s prime minus I prime is positive. So that means the t prime plus s prime minus I prime is positive. So that means the denominator is positive. You have a positive number over positive number. The answer is that's positive. That's it. That's the answer. You guys see how we got that? How we got part C? We got part C by saying, okay, we got this f. We need to do this sort kind of flipping of the partial derivatives with the negative sign. Once you plug in what you find, you get this, and you can tell that it's positive because of this condition right here. Okay. By the way, it's fun to talk about this term here, dy star dg0, just for a little bit, because what that is what is the effect of raising government expenditure on national income? In this model, it's positive. What does that mean? This is sort of a macroeconomic theory that says, well, in times of recession where national income is particularly low, that's what a recession means, right? GDP is low, GDP growth is low. That's a recession. One way to increase at least the equilibrium Y star, that you're like pushing yourself towards a higher Y star, is to increase government spending because it's positive. I mean, assuming these assumptions are true, then because dy star dg0 is positive, this is an argument in favor of, let's say, Keynesian economics that says in times of recession, you increase government spending. This is a justification for that. So it's a little taste of macroeconomics in case you're interested. Do you guys have any other questions about this? I'm gonna wrap it up and admit Jordan. That's okay.
Are we able to send you revisions of number 2? If we just like messed up one part and it kind of messed us up for the rest of it?
Dang. The problem is I just told you exactly the answer. So if you do this, it's basically it's sort of weird to give you to give you a revision. You're just going to give me back exactly what I told you now, aren't you?
Okay. Well, I was just gonna like go over and I guess just change where I messed up, but yeah, I guess I get that.
I don't know. I guess I should have given you an opportunity to leave the Zoom so that you could have made your changes on your own rather than make the changes based on what I just said. I think that's the issue. I don't think it's fair to let you make the changes.
Okay. Yeah, I just didn't know because there's only 2 questions, so I thought that like because I messed up the second one, it's only like 50%.
What do you mean the second one, like B or A?
I guess yeah, A was correct. I just didn't eliminate the Y's. I thought I was solving for Y star, so I eliminated both the Y's, but then I just didn't set it equal to 0. I just set it equal to Y star.
Like you set everything over here equal to Y star?
Yes.
Where did the Y star come from?
That's what I did that's because I messed up my math, but I ended up eliminating it in part B and getting like coming to the right conclusion and doing it right, but
yeah,
I did part A wrong.
I know you guys are worried about the points and you want to correct your homework to get more points, but I think the best thing I can do for you is be as generous as I can with partial credit and say, assuming, even if you did make a mistake at one part, I'll look at what you did given that mistake in the rest of the parts. Does that make sense? And I don't want you to think that I'm giving Jordan this opportunity for like full credit turning it late. No, he's gonna lose a lot of points for turning it late too. So it's not like Jordan is better off than you. I don't think that's the case. I don't think that would be fair either. I think the fairest thing to do is reward people who turned it in on time. People who got it right, I want to give them as full credit as I can, lots of points. And then people who came close, I'll give you as generous as I can with the partial credit. But it has to be like separated somehow, just to be fair. Yeah, sorry about that, Colin. Any other questions about this before I close it up? It wasn't that hard, right? It was the hardest part. I don't know what you think the hardest part is, but I suspect the hardest part was figuring out what this formula here for f was, and then how to use it to solve this and this, these two things. Once you get this implicit function here, I think it's a lot easier to figure. Oh yeah, just use what we've been using. But it's like it's sort of a mental leap here to be like, well, what about t and s and I? And you have to be okay with the fact that you don't know t or s or I explicitly. You don't know them. That's okay. I'm asking you to solve it in terms of the derivative. So that's kind of the workaround here. Is even though you don't know I, s, or t, just pretend like you know their derivatives and then solve it like this.
Oh, Professor.
Sure.
So if you would have done by the multiplying the negative, you would have gotten a different. The formula would have been negative. So would the
No, it wouldn't.
it wouldn't?
I don't think so, because there would be there would be a negative on the top and on the bottom, and they would cancel.
Why would there be a negative on the bottom?
Because you're taking the derivative of this with respect to g0 and of this with respect to y star. The derivatives will flip on the numerator and the denominator, and those make negatives cancel. Trust me, it doesn't matter. It doesn't matter if you had negative, negative, positive, positive. You would get doing the same thing. You have this negative out front. The top would be positive, and this bottom negatives, and then this negative would cancel out. Those would be positives. You'd get exactly the same thing.
Okay.
And maybe you did. Maybe your answer
Yeah, I
is
just
correct.
I didn't distribute the negative. Yeah.
Yeah, something like that.
Okay.
It really doesn't matter though.
Okay.
As long as you have something equal to 0. Something equal to 0, then you can start using this. It's really the corollary, right? It's the corollary to figure out things like dy dg0.
And if you set it equal to f, would that be incorrect? Capital F.
Set what equal to f?
The
whole left side?
The whole left side.
Not only is that not incorrect, that is correct. That is expected.
Okay.
In fact, if you don't do it, I'll be generous, but it's nice. Like the fact that I'm using this capital F here, the only reason I can do that is because I've defined this whole thing as F. I didn't write that out because there wasn't enough space, but that actually has to be done, because otherwise, what am I talking about here when I say F G0, F Y star? It doesn't make any sense unless I've defined what F is. The definition of F is everything. Everything here on the left-hand side of this equation. Make sense, Jonathan?
Yeah. Thank you.
Yeah. But not only is it, I'm glad you did it. Any other questions? Yeah. Sorry if it was a tough homework assignment, but I got to challenge you sometimes, right? You guys normally do very well on the homeworks, and I appreciate that. So we'll see how you did on this one. If you didn't do as well, I wouldn't worry too much about it. As long as it makes sense now. If it makes sense now, then I think you're good. What do I want to do? Clear drawings. Close. And stop sharing and admit Jordan. I think that was more like a half hour. Welcome back, Jordan. I guess that was more like a half hour, but we are finished talking about the homework. And what I would like to do with the rest of the class is start the next topic, which is optimization when there's more than one choice variable. Something I've alluded to a lot in the past, but we haven't actually studied. So let's do it now. Where is it? Pardon me. It is, no, not there. Course documents. This one I have as a PDF for some reason. I think it's because I was on a MacBook and I didn't have PowerPoint when I made this. Okay. Once again, though, I would like to use full screen. What's happening? Sorry. I gotta figure that out. Okay, here we go. Let's share it. This is from Blackboard under course documents. There's a file called unconstrained optimization with more than one choice variable, and that's what I want to talk about now. It is a process that's quite important in economics. In fact, it's so important, you've probably done it already in some other class or maybe something similar to it, if not exactly this. Why is it so important in economics? Well, this is really not ideal, is it? You'll only see part of the screen. If I download, and then no, sorry. Shoot. Okay, you can't see this whole slide. Can you? I want to maybe download it and then open it as something full screen.
You can change the percentage too, and it'll zoom out.
Yeah, is it like F11 or something? That's
It's
yes.
like a little black bar there. Yeah,
It
right.
is F11. I figured that out. Let me do a new share. This one. Is that it?
I just see like the mouse up at the top, and it looks like you could probably just click on that 100%.
How about this one? Are you seeing the full screen now? Oh shoot. Stop share. Screen share. This. Right? You see it?
Yeah, I can see it.
Okay, like on the screen now it says complex optimization problems in economics.
Yep.
And then a two choice variable problem structure. So let me just take a second or two or a minute or two to talk about some of these problems have multiple choice variables in them. And that is why you need a new mathematical tool to solve them. Because, let's say you're a firm and you're trying to maximize profit, but there are multiple prices you have to choose. You're not just selling one thing at one price, you're selling multiple things at multiple prices. Or quantities, I'm choosing multiple quantities, or maybe I'm choosing a price and a quantity. In either of those cases, there's more than one choice variable, and so we can't use what we learned in the first half of the class, which was, just take the first derivative, take the second derivative. If it's positive, that means it's a minimum. If it's negative, it means it's a maximum, that sort of stuff. It won't work when there's more than one choice variable, and that happens with profit maximization or cost minimization. Obviously, a firm wants to minimize its cost, but it might have more than one input to choose. Capital and labor, for example. I'm choosing capital, I'm choosing labor, but I want to minimize the cost. Even consumers often need to optimize. You can choose different products as choice variables, and I'm not just deciding, let's say, how big of a house I want to live in. How much do I want to spend on housing? I'm also choosing how much do I want to spend on food and entertainment and books for college classes. I'm choosing all of these things at once, and therefore the optimization problem of how should I choose all of this stuff is something with multiple choice variables. And of course, utility optimization is what I would call a catch-all. It could be anything. You could be optimizing. Utility is just a way to measure what's your most preferred outcome. The thing that gives you the maximum utility is the thing that you prefer over all other outcomes that are feasible. So that's what utility optimization is. It could be pollution, it could be hours of leisure time if you're labor. If we're talking about labor economics, right? People decide I want to work given a certain wage, but I also want to have some free time. I don't want to work 12 hours a day. That's just so much time. I don't get any leisure time. So, maybe you've never seen this before, but in the world of labor economics, I'm not a labor economist, but I'll say they sometimes have this fundamental problem of a worker who is facing a choice between taking on a job, taking on so many hours and getting the wages and the benefits from those wages versus not working and taking fewer hours and consuming those hours of leisure. Even this is like a new way of thinking about you as a worker being willing to work. Why are you willing to work? Well, there's this trade-off between leisure and consumption that I get from the dollars I earn in the wages. And once again, that's a problem that where you need this source of technique, multiple choice variables. Okay, so let's try it. Enough trying to convince you that it's worthwhile to study. Here's a very simple problem structure. There's two variables, x and y. It can be any real number. We're not talking about imaginary numbers yet, or perhaps at all. Will we talk about it at all? Probably not. Depends on how much time we have. Objective function, that's the thing you're trying to either maximize or minimize. Your objective as a decision maker is to either maximize or minimize a function, and we call it the objective function. So the problem looks like this. Remember, right underneath the word max or the word min is a description of the choice set. And if you remember, often in the first half, it was an interval. It would be x is an interval, like let's say 0 and 10. That's what I used a lot. And you were only allowed to choose x's between 0 and 10. But now, for right now, let's say you don't even have these constraints between 0 and 10. You have the whole real number you can pick for x. You have the all real numbers you can pick for y. This is sort of an unconstrained problem. And this is what it would look like. No questions about that, right? It's just telling you what it looks like.
I'm gotta leave now, by the way.
Okay.
But
Yeah.
I'll catch up on the video if you upload it to
Yeah,
YouTube.
you know what? I'll record and it should be on YouTube. So
All right. Thank you.
yeah, good luck with the vaccine. Even though maybe I shouldn't share that, that's private, especially on YouTube. Don't pay attention to that, anybody who's watching. Okay, first order condition for two choice variable optimization. So here's a problem. As I said before, this is a very generic way of writing the problem. F is our objective function, x and y are our choice variables. We can already say something about what must be true, what condition must be true in order to optimize. And that is some point, x star, y star. Remember, the stars indicate that they're like not just any x, not just any y, but special points that are actually the maximum, or at least a local maximum of this function. This point, x star, y star, can be a local maximum or a minimum if the partial derivatives f sub x, f sub y are both equal to 0 at x star, y star. Remember, this is very similar to the first order condition when there was only one choice variable. For that, it was the derivative of f. It wasn't a partial derivative. It was actually just the derivative of f had to be equal to 0. Well, now we're not saying the derivative has to be 0, but the partial derivatives of each variable have to be 0. Okay, that's what the new first order condition is. All partial derivatives have to be equal to 0. Just for clarity, sometimes I will call FOC1 the first order condition for the first choice variable. In this case, they're listed x first, then y. So FOC1 in this case is simply that the partial derivative of f with respect to x is equal to 0. That's what I mean by FOC1. And if I say FOC2, of course, that means for the second choice variable, the derivative of the objective function, partial derivative of the objective function with respect to that variable is equal to 0. In this case, f sub y equals 0. I say in this case because it won't always be x and y. In this case, x and y are the choice variables, but it could be anything. What if it was like profit? And what if it's quantity, right? You have Q1 and Q2. Maybe those are the choice variables. Or maybe it's a profit, maybe it's a cost minimization problem and the choice variables are K and L. K for capital, L for labor. That's possible too. try to be okay with this flexibility and say, no matter what problem you give me, I can tell you what the first order conditions are. And it's that the derivative, partial derivative of the objective function with respect to each choice variable is equal to 0. Any questions about that? It sort of makes sense, doesn't it? If the partial derivative were not equal to 0, then how could x star y star be a maximum or a minimum? Because I could just increase x. Let's say fx was greater than 0, and I'm looking for a maximum. Well, why don't I just increase x a little bit? If I increase x a little bit, I should be increasing my objective function, and just leave y the same. I won't change y. All I will do is change x a little bit. And if fx is positive, that means I can increase my objective function. Similarly, if fx is negative, that means I can decrease x a little bit. Maybe already you can see that the derivatives have to exist for this to be the case. We have to, let me be more clear. This first order condition, it only applies to differentiable functions, functions which can be differentiated with respect to each variable. If for some reason the function were non-differentiable, these first order conditions, I guess, just wouldn't apply. Okay. I think in this class, I'm going to give you differentiable functions. Why wouldn't I? I sort of don't want to bother with that other case. Okay, I think we're ready to talk about second order conditions. Second order conditions are going to be different for maximization and for minimization. So let's talk about maximization first. In between here. If my problem is to maximize f, given any choice for x and y in the real numbers, the first thing you have to do is satisfy the first order conditions. That's why they're called first order conditions, because they're the thing that you check first. Once you've checked the first order condition, then you can look at the second order condition. What will it be? Well, if some x star and y star satisfies the first order conditions, I should have said plural here. I don't know. It's sort of ambiguous whether this refers to both or one, but it's okay. Then it will be a local maximum if the second order partial derivative fxx less than 0 at x star y star. So this is the second order partial derivative. I take the partial derivative with respect to x, and then again with respect to x, it has to be negative. Also, the determinant of the Hessian matrix has to be positive at x star y star. And another way of writing this is equivalent to, this is basically the determinant of the Hessian right there for two variables. And you might hopefully make some connections here. You recognize this is the same thing for local, is it concavity or convexity? Local concavity or local convexity is equivalent to this condition here that I've written down. Notice that the partial derivative is negative.
Would it be convexity?
I'm sorry.
It's okay, it's a 50-50 shot.
It was a 50-50 shot. Hey, I'm glad you said something. It's better than everybody else who said nothing. The answer is concavity. So just in case you forget, anytime you forget this, and like, which one is it? This is concave, right? It's like you're inside of a cave. And this is when the second derivative is decreasing. See how it's the first derivative is positive, then 0, then negative. Okay, so that's concave. It's f double prime negative. It's concave. So because this here is fxx less than 0, that's why it's equivalent to concavity. If it were look, if it looked like this is f double prime positive. I don't know if there's any way to sort of If there's any mnemonic to think of this as convex, like, I don't know, why is it convex? It just is. So yeah, the second order condition for maximization is really just equivalent to saying f is locally concave at this point x star y star. If f is locally concave at x star y star, then think about some point at the top of this cave, the top of this function. Yeah, that's going to be the maximization, which is what you're looking for. You're looking for maximization. It's this point right here at the top of the cave, which only happens when f double prime is less than 0. So f double prime less than 0. Here, it's not double prime, it's xx. Does anybody think it's weird that there's no fyy? I've spoken about this already, but some of you may have forgotten. Why don't we also have to check fyy? Shouldn't we say, well, fyy should be less than 0 too, otherwise it's not going to be a maximum. That's true, fyy should be less than 0. However, it's built in here. It's kind of handy that this will only be true when fyy is also negative. Because if fxx, if this is a negative, then this has to be a negative times a negative in order for this whole thing to be positive. So logically, these two statements can only be true if fyy is itself negative. That's why you don't have to check it. It's not that it doesn't have to be true. It does have to be true. You just don't have to check it. Okay? So the second order condition for two choice variable maximization is it has two parts. It has fxx less than 0, and it has this part down here, which is that the Hessian the determinant of the Hessian should be positive. That's really all you have to remember or do for problems like this. I'm going to delete all of my drawings because they're messy. Now let's talk about minimization. You guys have any questions about max? These sort of conditions for maximization. I want to speak more later about where this determinant for the Hessian comes from, because if you've never seen this before, it seems arbitrary. Like what does that have to do with maximizing an f? Like like let's say f is profit. Let's say f is profit, and you just want to maximize profit. Like, okay, I'm going to try to make as much money as I can. What is all of this? What does all this complicated garbage have to do with making profits? fxx, fyy minus fxy quantity squared. Why does that being positive affect me? I'm just a business owner trying to make as much profit as I can. There's a reason. I can sort of explain, but sort of can't because it's three-dimensional and I can't draw that well in 3 dimensions, but I'll try to explain. Okay. All right. Next slide. The next slide is going to be about minimization. Good news is it's almost exactly the same. What if instead of maximizing, we want to minimize some function like cost? Cost is something you want to minimize, or pollution is something you want to minimize, or the number of people who die from some kind of disease. I know that sounds horrible, but there's sometimes public health officials have to work with variables that are very personal in people's lives, and it's like that's their job, is to say, let's try to do whatever minimizes the number of deaths or hospitalizations or something like that. So minimization problems, they're important too. What would be the second order condition for that, for minimizing? Well, it's the opposite direction of this derivative, just because of what I was saying before about concave or convex. You should think of concave as being the top point of a hill, which is where maximization occurs. And you should think of convex as being the bottom point of a valley, which is where minimization occurs. So that's why fxx should be positive for minimization. What about the Hessian, the determinant of the Hessian? Does that flip sign? The answer is no, it does not flip sign. In both cases, the determinant of the Hessian should be positive. So let me just, I'm going back to annotate. I'm sorry, I like annotate so much. But if f of x is positive, what has to be true for this Hessian determinant of the Hessian to be positive? This term has to be positive. Of course, this whole thing will be minus a negative. So in order for this whole thing to be positive, these better both be positive. Right? Positive number times a positive number. That means, just like before, there's this implied condition that fyy is greater than 0. You don't have to check it, but it must be true. It's built in. Okay, so now we have the first order conditions for maximization. That's fx equals 0, fy equals 0. We have the second order condition for maximization. That's fxx negative and determinant of the Hessian positive. And we have the second order condition for minimization, which is fxx positive and determinant of the Hessian positive. If you could just sort of remember all that stuff, or you know, internalize that, that'll get you pretty far in these problems. You know, kind of all I'm really asking you to do. I'm asking you to know that and to be able to interpret it for whatever problem I give you. I give you a problem and you have to use that to solve it. And we'll probably do that for a week. I don't know, a couple more classes. Oh, by the way, I do want to have a quiz. Not me, the syllabus claims, and I'm sticking to the syllabus, that there is a quiz on April 8th, which is a week from today. So a week from today, I'll give you, I think, you know, a quiz. It's probably going to be like one problem about the implicit function theorem and one problem about optimization with two choice variables. So plan on that in a week on Thursday. I'd like to have an in-class quiz if that's okay. If I think it's like too hard and the time is an issue, then I'll give you more time and make it be like a take-home. But I think I can write it in such a way that it won't take you more than 20 minutes. You know, maybe I'll plan for it to take 20 minutes and I'll give you 30, just like, hey, you can have extra time. But I'll let you know as we get closer whether it will be in class or maybe even like a take-home quiz. But it will be on Thursday, next Thursday. Okay, next slide. Ooh, this is a good slide. Why are these second order conditions more complicated? Well, you know, in one dimension, the graph of fx either looks like a hill, and if you're maximizing, you just choose the point at the top of the hill. That's what I've been talking about already. But with more than one dimension, this function f, which is now a function of x and y, it might look like a hill in the x dimension. That's good. That makes the top of the hill you think would be the maximum. It might also look like a hill in the y dimension, which is good. It's like, okay, the top of the hill in the x dimension is good. The top of the hill on the y dimension is good. Aren't we good? Those are the only two dimensions, x and y. That means this has to be a maximum point. No. Even then, it doesn't mean the top of the hill is the maximum. What? Mind blown? The reason is there could be some other direction in which the top of the hill becomes the bottom of a different hill from a different perspective. That's what we might call a saddle point. A saddle point is like a point where the first derivatives are all 0. The first derivatives in any direction you look, the first derivatives are 0. But the second derivatives change in sort of interesting ways. In fact, they flip the sign. Sometimes they're negative, sometimes they're positive. And therefore, the point isn't really a maximum. There could be some other point that's a better maximum. Or just simply, it's not a maximum. And how do you need to think about that is by thinking of the cross partial derivatives. Those are these partial derivatives that are like f of x and xy. fxy is what we call the cross partial derivative. I have a little graph of this, if you don't mind. I'd like to maybe share. And it's not some complicated program. Where did it go? It's just a F11 maybe, 3D graphing calculator that I found online for free. It doesn't work that well, but it works well enough. Here it is. Something called geogebra.org. These websites are always changing. So look what I have drawn. I love how it spins too. The spinning is kind of cool, even though not much is changing here. You can see this function that is being drawn in 3 dimensions, right? I have it written here. This is the function f equals x squared plus y squared. And it kind of makes sense, right? If you look at it just like here's what it looks like just in the x-axis. It looks like a parabola, x squared. Here's what it looks like just in the y-axis, also a parabola. The whole thing just looks like a bowl, doesn't it? And if somebody asks you what's the minimum point of this function, it's really easy to tell. It's this point here, 0, 0. It's obviously at the bottom of this bowl. I've made it spinning now. This spinning bowl has this point in here. And if you thought about the second order conditions, they would be pretty simple because the function's x squared plus y squared. Fxx is simply 2. Fyy is simply 2. Both of those are positive. That tells you it could be convex. And then if you took the determinant of the Hessian, it would be 2 times 2 minus 0 times 0, it would be 4. It would be 4. So this meets all of those second order conditions for minimization at this point, 0, 0. Does that make sense? Maybe I can annotate a little bit here. Look, here's the function. So fxx equals 2. That's supposed to be fxx. This is supposed to be fyy equals 2. So you know, we check off this thing for the second order condition. And what's the determinant of the Hessian matrix? The determinant of this matrix, which is 2, 0, 0, 2, which is 4, which is positive. So check that off. The second order conditions for minimization, not maximization, but for minimization are met at this point here, 0, 0. Does that make sense? And the graph kind of, it's obvious when you look at the graph. It's like, yeah, that makes sense. I can spin it. You can see there's no other point. You can even see it top down. That's kind of cool. But you know, it's definitely the minimum. Okay. Now I want to change something about this function. I'm going to clear all my drawings. And what I'm going to do is add something in the cross partials of this. What are cross partials? Things that when you differentiate with respect to x and then with respect to y, it still remains. So it's going to be like a term that has an x and a y in it. Something like, how about plus xy? Okay. What would the Hessian matrix for this look like? Well, it would be 2, 1, 1, 2. Do I need to write that out? Maybe I'll write it out in a T. The Hessian matrix now is, because I've added this xy term. Can you see that? X squared plus y squared plus xy. If I take the cross partial now, it's equal to 1. So this would be 2, 1, 1, 2. I don't know if you can tell, but this, but the determinant of that is still positive. The determinant of that is still positive. It's 4 minus 1 is 3. So we're actually still good. We're still good now. That's a check mark because we can still say that this point 0, 0, is it 0, 0? Gosh, now I'm starting to doubt that. I think so. Yeah, I think it's 0. Is still the minimum. I'm gonna exit out of this and give it a spin. Yeah, you can still see that point 0, 0. We're still fine. The second order condition here has still been met by adding this plus xy. What if though the cross partial gets bigger and bigger so much that the determinant is no longer positive? What would that look like? It would look like this. I'm going to now change it instead of plus xy, I'm going to change it to plus 3xy. Okay, that's all I'm doing is I'm just adding a coefficient of 3 to this xy term. Here's what happens. Wait, that's not what I thought would happen. Oh, there we go. Look at this. Craziness, right? What's happening now? Let's talk about the Hessian. Let's talk about the Hessian. Let's erase these ones and replace them with threes. 3 here, 3 here. Now the determinant is 4 minus 9. 4 minus 9 is -5, which, you know, maybe I should even do this in red. Bah, it doesn't pass the second order condition anymore because of this cross partial term. What does that imply about the graph? Well, take a look at it. This was kind of the whole point. I don't know why this is, I want that to go away. Okay, so now if I give it a spin, can you see how sometimes it looks like it's convex and sometimes it looks like it's concave? Like there, this looks like it's convex, right? Like it's the bottom of a hill. But oh, now it looks like it's concave. Like it's the, I said bottom of a hill, I meant it's, no, wait a second. Yeah, the function looks like a, I guess you would call it a valley is what you would call it. Like a valley, and it's at the bottom of the valley or a bowl. But if you spin it a little bit and you get this way, now this function looks like a hill and you're at the top of the hill. And you know, what's going on? Is this function a hill or a valley? The answer is it's sort of both. It's a saddle point. I don't know if you can even make sense of this from the spinning. I can. I mean, it's weird enough that I don't know. What do you think? I can make sense of that. But surely you can tell that this 0.00 is no longer a minimum. If you're trying to minimize this function and you said, well, 0 really seems like the minimum point here, you'd be wrong, because there's some ways that you could move to get a lower value. Okay. Like if you're trying to minimize pollution or something, you think, okay, the lowest pollution we can get is here at this 0.00. Well, that's not true. You can tell that I don't know if you can tell, but it definitely goes down into the negative values here. Okay, so the lesson is this Hessian matrix really tells you a lot about what's going on at any particular point. It's in fact, because the determinant became negative, let me rephrase that. The reason the determinant became negative is because these cross partial terms became so relevant, so significant. And that comes from this extra term here, the plus 3xy. And that's saying like, wait a second, like what if, you know, x is negative and y is positive? That means this whole term will be negative. And in fact, it could be so negative that it overwhelms the positiveness of the x squared and the y squared. That's what it's saying. It's saying I can actually make f even lower than I can when I let x equals 0 and y equals 0. And it comes from this cross partial term, which makes itself known here in this cross partial part of the determinant, which makes itself known here by making the determinant negative, which is where the red x comes from. It's not a perfect illustration, but hopefully that's an illustration of like where the weirdness comes from for these multi-dimensional functions. You would never have this in one dimension. If you were just talking about one dimension, you would never have this. It's either concave or convex at a point. You don't get this like, there's no way to spin. There's no way to spin a one-dimensional, it's actually two-dimensional, one x value and one f. Okay, hopefully that point is made clear. Probably spent too long on that, but it's something I think is kind of fun. We don't have much time left. Do I have anything else I want to share with you? Let me think about the slides I have so far. And I have an example, but do I have enough time to go through the example? How do you guys feel? You want me to go through an example or wait till next class? Any thoughts? Here's the example. I'll show you the example. It's simply a quadratic objective function. It's not complicated. how about we compromise and say, if you want to give this a shot, and we'll explain the answers next class. I'll even tell you how to do it now. Let me tell you how to do it. Take the derivative of this with respect to x, right? That's going to be the first. Oops, I'm red. Right, first order condition. The first one, FOC1, is going to be the derivative of this with respect to x. And you want to set that equal to 0. Oh man, I'm doing it. I said I wasn't going to do it, but I'm doing it. Minus 4x plus 2y plus 5 equals 0. That's FOC1, isn't it? Put a colon here. FOC1 is that the first choice variable, which is x, the derivative of the objective function with respect to that choice variable has to be equal to 0. And I've written that here. What about FOC2? Okay, well, that's the derivative, partial derivative of the objective function with respect to the second choice variable has to be 0. Well, you can calculate that as just negative 6y plus 2x. Sorry, plus 2x equals 0. Got that. How do you solve this problem, though? You actually need to find x and y given these two equations. It doesn't just tell you x. It doesn't just tell you y. You actually need to find them. You need to calculate them. This is part of the reason I gave us some practice with how to solve a system of equations here. That's all this is. It's a system of two equations. Use substitution if you want. You could use Kramer's rule if you want. I don't think you need Kramer's rule, but let's say there was a third choice variable z, then maybe you would want to use Kramer's rule. But for this, I don't think you need it. Just use substitution. Solve for y in terms of x, and then plug that in, and then you'll have an equation with only x's, and you can solve for x, and you can go back and solve for y. That's going to be the method. That's going to be the method for finding a potential solution to this maximization problem. Here's a problem. I want to know the solution to this problem. Well, the first step should be write out the first order conditions and attempt to solve them simultaneously. Then you have a potential solution. Is it an actual solution? That's when you need to look at the second order conditions. And remember, they're a little bit more complicated now. You need to see that fxx, it should be positive or negative. Should fxx be positive or negative? Uh-oh.
Should be negative.
Correct. Because we're doing a maximization, it should be negative. Thank you. So you need to check that. And then you also need to check that determinant of the Hessian should be positive or negative. I'll just tell you it's positive. Okay. So if you found a solution to this system of first order conditions, meaning that you found an x and a y that solves both of these equations simultaneously, and then you find, given that x and y, that these second order conditions hold, that means you have found a local max of this problem. Yeah, I should stop there, but just one more thing. Because this is a continuous function in differentiable, twice differentiable, and anyways, we can say that this, if there is a global max, it has to be this one that we would find, right? I can talk more about this later, but when you're solving a problem like this, you don't want to just find a local max. You actually want to find the global max. I will explain, just some ways to guarantee that, yes, this is indeed the global maximum of this function. We'll talk about that next class. So thanks, guys. Do you guys have any questions? Stop share. Anybody have any questions about stuff? We'll do a quiz on Thursday. All right, I'll see you guys next week. Have a good weekend.